Hi. Right. Good to see you back. Okay, so it is 3 o'clock, so I do want to get going now. Um, First of well, what we're planning on doing is going over different things in terms of the structure, how to draw molecules, and so on. And then we'll go on to the different types of isomers. So the first section is really important also for your internal standard, as well as for the exams. Okay, let's just look at these functional groups again. Do you remember all these groups? So the alkane, just C and H bonds, all single. Alkene, a C-C double bond. Don't just say double bond, because you know two different types of double bonds now. You know the carbon-carbon double bond as well as the carbonyl one, the CO double bond. Okay, the haloalkane, it just has the chlorine. Great. Do you find the Quizlets help you, April? Yep. Okay, it's a sort of fun way, especially when you play the games, the scatter or the gravity. It's sort of just repetition, and it's a bit more fun than just trying to memorize it. Okay, and amines, as I say, remember the Ni backwards for nitrogen to help you remember the amine as an NH2 amide. Think of the D for the double bond. So amine is similar to amide in terms of the name, so it has also the nitrogen, but the D is for the double bond. And then the acyl chloride, it's the chlorine, and it's different from the haloalkane. Acyl, another way of saying C double bond O, we can talk about carbonyl or acyl, same thing really. So it has that double bond in it. Okay, so those are like fundamental for organic chemistry, so make sure you keep on learning it until you know those off by heart. There's 11 to learn, so it's not too bad. Okay, these are just the little tips that we had to remember. Okay, and then what we also did last time was the code. To crack the code, remember those different bits. The end is always the major functional group. Then we have sort of in the middle is the number of carbon atoms. So we've got 4 carbon atoms. The black over here tells you whether there are any carbon-carbon single bonds, double bonds, or triple bonds. So if it's only carbon-carbon single bonds, it's N. If it's double bonds, you'll have N or EN for the double bond. And if it's a triple bond, which you don't do at level 3, then it would be EIN. Okay, so that's what that code bit there does. And then you've got any substituents in this front part. So substituents, number of carbon atoms in parent chain, functional group. So it doesn't matter what the double bond goes to. Well, the double bond would have to be in the parent chain. So say we had an alkene with an alcohol. The parent chain would have to have both functional groups in it, the carbon-carbon double bond as well as the OH group. But you would give the OH the lowest possible number. Does that answer your question? I'm not quite sure if I did. So the carbon-carbon double bond can be bonded to any other functional group. But if you have a carbon-carbon double bond, then it's an alkene. So I know you're typing there. Yeah, look, you can get a lot of other functional groups that you will learn at uni if you continue with chemistry. There's amines and amines and all sorts of things. Nitriles, that'll be a C triple bond in. You can get C double bond in. I don't think you can get a C double bond S. I don't think that happens. But you can get a CS single bond. So yeah, organic molecules are very weird and wonderful with lots of variations. But we just stick to our 11 functional groups for level 3. Okay, right. So those, just very quickly, this is just simply revision of what we did last time. It's always the functional group, longest continuous chain. See if there are any, for the black, if it's butanol or butenol or so on. And then you look at the side chains and you check where the side chain is. So always follow that pattern, always have hyphens between numbers and letters, have commas between numbers, and every side chain and every functional group has a number. The only time you leave out the number is if there is no other possible position. So for instance, propanone is a ketone, so that it's a C double bond O that has to be attached to 2 other carbons. And seeing that propanone only has 3 carbon atoms, the double bond, carbonyl has to be in the middle. So you wouldn't say ever 2-propanone because the 2 is redundant. You know it has to be in the middle. Okay, or if this was methanol, you wouldn't say 1-methanol or methan-1-ol, because obviously if there's only 1 carbon atom, it can only be on that carbon atom. So do you see what I mean when I say when you have numbers and when you don't? Yeah. So if it's totally obvious, there's no other choice, you don't have to put the number in. If there's any other possible choice, you put the number in. Okay, so that's, sorry, I forgot to put that down. Okay, now drawing. It's important, I think, unless you've done level 2 and you've done it well and so on, to always write full structural formulae. In other words, write each atom and draw out the number of bonds around it. Don't say CH3, CH2, CH2, CH2OH or something like that, because you're more likely to make mistakes. When you've got, you've really got it clear in your head, then you can start taking shortcuts. So you start off pretty much, okay, here's an example. You've got bute, so it's 4 carbons in a row, 1, 2, 3, 4. Then you have to put in the functional group. And what is the functional group in this case? So do you want to have a go? If it's 2-chloro-3-methyl-butene, what would be the functional group? Hi, Joe. Okay, methyl is a side chain. So remember what I said with the functional group, it always comes at the end of the name. So it's ene, and ene is our coding for a carbon-carbon double bond. Yep. So, and as I say, I'm pointing out it's carbon-carbon double bond and not a carbon-oxygen double bond. So it's on the second carbon. So it doesn't matter if we count 1, 2, or we could go 1, 2. So either way would work. Right, then the next thing is you draw the side chains. We know on the third carbon is a methyl group, and on the second carbon is a chloro group. So these are our 2 side chains. So we have the chlorine and the methyl. Now it's really important because it does depend on your examiner, but some examiners are very sticky about this. You must join the bonding atoms, and I have heard of students not being marked as correct if you make your bonding line sort of hover between the C and the H, or even on the H. That's marked as incorrect, because that bonding line shows that the carbon is bonded to this carbon. It's not that the hydrogen is bonded to the carbon. So be very clear where you draw those lines. Don't be just slapdash. Okay, so when you've got your side chains in and you've made sure you've joined the lines to the bonding atoms, this one's easy because chlorine is just 1 atom, so can be anywhere along there. Now you fill in your number of hydrogens to fill it up, and you make sure every carbon has 4 bonds. If you have nitrogen in the compound, it has 3 bonds, and oxygen has 2 bonds. Chlorines, fluorines, all the halogens, and hydrogen are 1 bond. So Okay, I was just highlighting the being drawn there, so I'm just adding the hydrogens. Why don't I add a hydrogen to this carbon over here? Or to that one? It's already got 4 bonds. So if you draw out the full structural formula like that, it's actually not full structural because I've made it semi-structural here. But if you draw it out in full and you count your number of bonds, you're less likely to make a silly error. So I really recommend like this. Perhaps with the side chain CH3 you could get away with, but even then you might want to put this in your lines, 3 lines around here with 3 hydrogens. Okay, and as I say, check the number of bonds because that's a really common error. So here's example of, you'll find you might get a question, draw a branch chain isomer of this molecular formula, or draw a straight chain. So little things like tertiary, secondary, primary, straight chain, branch chain, you need to know what it means because you could be asked to draw a particular isomer that way. So is this first molecule here on the top left, is that a straight chain or a branch chain? Straight. And we know it's straight because it's got no other substituent in it. It's got a chlorine. The chlorine could be sort of anywhere, but really we draw that line along there, it's straight. Now it could bend, but as long as it's a continuous line, that's what we mean by straight. What about this one over here? We've moved the chlorine from there to there. Is this straight chain or branch chain? It's straight as well. Okay, so we draw a continuous line. It doesn't matter that the chlorine's on there, it's still. And you know that it's straight because although I've got 2-chloropentane, I haven't got 2-methyl 2-chloro or 2-chloro-2-methyl butane. It's still a straight chain. I've only got pentane. I've got no other alkyl side chain. What about this one over here on the middle left? It's a bit of a trick one. Now just branched is the opposite of straight. So branched, if you were naming it, you would have a side chain name like 2-methyl something or the other. And remember, you can never get 1-methyl because 1-methyl means that methyl is actually part of the parent chain. So we actually have got a straight chain, because those single bonds can twist and turn, so it doesn't actually ever look straight as in a straight line. It could be, it's normally zigzag, quite frankly. If it's in its lowest energy state, it'll be zigzag. But you can, in fact, these very long chains with a few oxygens on each end, they can actually fold themselves up, so they can mimic estrogen, for instance, even though they're supposedly a straight chain of sort of 9 or 10 carbon atoms. So April, yes, this methyl group over here is actually part of the parent chain. And what is to say, one way is to name it, and if you ever land up with 1-methyl or 4-butyl, in other words, 4-methyl butane, so it's at the other end, you know that you've counted really the parent chain is a side chain. Okay, so this is going to be straight again, and it's 1-chloro. Exactly, these two molecules are exactly the same because these single bonds can swivel around. Okay, what about this middle right one? Is that branched? Or okay, Joe, you ahead? Great, it is branched. And the way you know it is if I run my line across it, my finger across it, I have to lift my finger to go here. You know, if I go up there, I backtrack. And to get a parent chain, you're not allowed to backtrack or skip. So that's my parent chain, and that is my side chain. So yes, that is, well, it's not quite 2-methyl. Oh, hang on, I think you were. 2-methylpropane. This is not actually 2-methylpropane, in that you've got 4 in a row, so it's butane, and you've got two substituents here. You've got the methyl and the chlorine. Yep. And so remember what I said, when you start counting, you always give the lowest possible substituent number. So if I count from this end, it's 1 chloro, and if I start from this end, it's 2 methyl. Now 1 chloro is lower than 2 methyl, so it would be 1 chloro 3 methyl butane. Do you follow that naming pattern? Yep. Okay. And then what about this bottom left? Is it straight or branched? Straight. Well done. Okay, because I can run my finger along here and I don't have to backtrack or jump or lift or anything like that. So it's straight, and it's just simply 3-chloropentane. And the last one, is it straight or branched? Branched. And if you run your finger along, there's no ways you can get to that methyl group without backtracking or jumping, so you know it's branched. And that would be 2-chloro, 2-methyl. So notice the 2 branched ones always have this -yl side chain, methyl or ethyl or propyl, but these are side chain. None of these others have that. They've got a chloro as a substituent, but not an alkyl. So a branched compound also always has to have an alkyl side chain. Okay, so you think you're pretty clear between the difference between straight and branched? Yep. Okay. Right. Now this is a revision of what you did last year, but you also need it for this year. Do you know the difference between primary, secondary, and tertiary? Okay, so not clear. Okay, primary carbon atom, it's attached to one other carbon atom, or possibly no other carbon atom, but it's up to 1 carbon atom. Secondary, it's the secondary carbon atom is to 2, and tertiary is to 3. I think it's fairly clear: 1, 2, 3. Primary, secondary, 2, tertiary, 3. Okay, so that would be an example of a primary alcohol now, because the OH is attached to this red carbon, and this red carbon is only attached to 1 more. No, tertiary is 3. If you go more than 3, it's quaternary. So if your carbon atom is attached to 4 carbon atoms, it's a quaternary carbon. And you can't get a, what would it be for pent? I mean for 5. I don't know. Anyway, yeah, so it's basically primary, secondary, tertiary, quaternary, quint. Yes, Joe, that would be quint is the next one. It's not quaternary because carbon can only have 4 bonds, remember, so you would stop at quaternary. Okay, so this carbon has got the OH functional group on here, so this is what we call a primary. The degree sign is just to say it's primary. So it's a shorthand way of saying primary to differentiate one from any old one, or first, or that first, second, third, because that's not the same thing as primary, secondary, tertiary. So we just put in the degree sign. This is the shorthand version. Okay, so secondary, here this is what we call a secondary alcohol. Okay, so Joe, this I've made the carbon that we're looking at in red. So my functional group in this case is an OH, so it's on this red carbon, and remember we always hone in on the functional group. That's always the most important. So we say this would be a primary alcohol because the carbon to which the OH is attached is only attached to 1 other carbon. This alcohol is what we say secondary because the OH is attached to this red carbon, and the red carbon is attached to 2 other carbon atoms. And then this is what we call a tertiary because the OH functional group is attached to this carbon, which is attached to 3 others. That's why we don't really get quaternary compounds as such. You know, you only hear about primary, secondary, and tertiary because carbon can only form 4 bonds, and the functional group has to be attached as one of those bonds. So carbon's only left with 3 bonds to bond with other carbons. Okay, you can get quaternary for nitrogen, and we'll look at that if you're interested separately. Okay, so those, Joe, do you get that now in terms of the primary, secondary, and tertiary? So you look for the carbon that's attached to the functional group, and you count how many carbons are around that particular carbon. So this is now the nitrogen. You expect it to recognize primary and secondary nitrogen compounds. OIC stands for? Sorry, you've lost me there, Joe. OIC, I'm thinking of like pentanoic acid or something like that. Oh, I see. Right. I've got chemistry on my brain. I was saying OIC, so do you mean like butanoic acid or something like that? No. Okay. Now, when the ones you're going to be coming across as primary, secondary, tertiary functional groups will be the haloalkanes and the alcohols, and then the amines. Now, how many bonds can a chlorine form? The chlorine, 1. Okay, it's got it's got the valency of 1. It's got 7 valence electrons, so it'll gain, and so it's got a valency of 1. So it can only form 1 bond. So we can't have primary, secondary, or tertiary based on the chlorine, because the chlorine can only ever form 1 bond. So it doesn't matter where it is, it can only form 1 bond. And that's why when we talk about primary, secondary, and tertiary for alcohols and for haloalkanes, we look at the carbon that is bonded to. Because in OH, I know oxygen can form 2 bonds, but 1 will be to the hydrogen, so it's only left with 1 other bond to go to the carbon. So this could have been a chlorine in each case, and we'd still have the same primary, secondary, tertiary. Nitrogen, though, can form how many bonds? It's got 5 valence electrons, but its valency is going to be 3. Yep. So it can, if it uses its lone pair, form 4, but if it does that, it's going to have a positive charge because it's shared its lone pairs of electrons. So nitrogen forms pretty much 3, and then, as I say, you can push it to form 4 bonds, but then it will have a positive. So because of that, if a nitrogen is bonded to 1 carbon, it's primary. If it's bonded to 2, it's secondary, and if it's bonded to 3, it's tertiary. So that is primary. This one over here that I've just put up is secondary, and that is tertiary. So the reason why it's got a different counting system is because OH can only form 1 other bond. Chlorine, iodine, bromine, fluorine, they can only form 1 other bond. So we have to have a different naming system. Whereas nitrogen can form 3 bonds. And as I say, you can force it for the 4th one, but then it becomes positive. So that's why primary here is when the nitrogen is attached only to 1 other carbon. Secondary is when it's attached to 2, and tertiary it's when the N is attached to 3. So you are expected to recognize that, but you don't have to name the systems for secondary and tertiary, because you do have a different naming system. Okay, you don't see the difference. Okay, with the OH, is the OH attached to 1, 2, or 3 carbons? Or is the OH always attached to 1? Okay. Here with the N, is the N attached to 1, 2, or 3 carbons? Yeah, so here it's 1, there it's 2, there it's 3. Whereas here, the OH can only ever be attached to 1 carbon. So what I'm trying to say is when I've got a haloalkane or an alcohol, I look at the carbon it's attached to before I work out if it's a primary, secondary, or tertiary. With an amine, I don't look at the carbon. I don't look at this one and say, it's, you know, if I look here, I can't say, this carbon's not attached to any other one, so this one's primary. Do you follow? With the amines, I don't look at the carbons and see how many other carbons it's been attached to. I just simply look at the nitrogen. You will, with practice, come across it. And as I say, you will never be expected to name a secondary carbon. You may be given one. You might say the compound below is 1-methyl N ethyl, blah, blah, blah. There you put in N's for the secondary and tertiary. But you won't be ever expected to name it. Right. So, very quickly, because time is fleeting, primary, secondary, or tertiary. What is number 1? So just say 1, 2, or 3. So look for the functional group. If it's a halogen or an OH, look to see how many other carbon atoms the carbon is attached to. If it's a nitrogen, you look to see how many carbons are attached to the nitrogen. Right, so the first one, the chlorine is attached to this carbon, so this carbon's only attached to one more, so it is a primary. Number 2, is this a primary or a secondary? It's a secondary, well done, so that's the carbon we're looking at. This carbon's attached to 2 others, so it's secondary. What about number 3, primary, secondary, or tertiary? Okay, you're going for 2? Okay, this is what we want. This carbon is attached to how many other carbon atoms? Yep. Okay, so it's only attached to 1, so it's primary. What about number 4? Primary, secondary, or tertiary? One, correct. Because you look for the functional group. With organic chemistry, you always look for the functional group because that gives its reactivity. And it's only attached to one other carbon, so it's primary. Number 5. Okay, good question. There is little, and we'll do this when we do reactions, there's very little difference in reactivity between the C here and the C there, because there's no difference in electronegativity. So there's not a stress point in the molecule where, say, there's a lot of electrons that's saying, you know, I'm very negative, come to me positives, or I'm very positive, come to me negatives. There's just a very even distribution of electrons, and it's all very much the same, and so it's not going to do very much. In fact, alkanes really do nothing except burn. They otherwise don't do much. You've got to do fancy things to them to make them react. If you've got a halogen attached to it, then you're saying, I'm more electronegative, I'm more negative, this carbon is more positive, so it's going to attract something negative to come and attack this carbon. You've given it a point of difference, you've put a stress into the system, and that's why you look for the functional group. Okay, so number 5, correct for secondary, because just highlight that one, it's attached to 2 other carbons, so it's secondary. And the last one, primary, secondary, tertiary. Okay, because there's the functional group, and there's the 3 carbons it's attracted to. Okay, so you think you can recognize primary, secondary, and tertiary? Yep. Okay, so now this is what you're going to need for your spectroscopy standard for the excellence part, because you need to be able to work out, does my formula match my structure? And one of the ways you do it is by checking what we call for the degree of unsaturation. So if it's unsaturated, it means it has a double bond, and it can be unsaturated and only have 1 double bond, or 2, or 3, or so on. So if you have a look at this, if I wrote the molecular formula for each of these, okay, but I've just to say each carbon has got 4 atoms bonded to it, so it's saturated. I cannot add any more hydrogens to each of these carbons because each of these carbons have got 4 bonds. So that's what I mean by saturated. And yes, unsaturated is the same thing. It's got a carbon-carbon double bond. So here this carbon is actually only attached to 3 atoms. So it's unsaturated. We can still add something to it. So we can add 1 more atom to this carbon and 1 more atom to that carbon. Okay. Oh, sorry. I'm getting ahead of myself there. So we've got no double bonds. So the formula is CnH2n plus 2. So if N is 2, like here, so Cn is C2, H2n, 2 times 2 is 4, plus 2 is 6. Do I have 6 hydrogen atoms here? Yep. Okay. So that's the general formula. You should have learnt this at level 2, but level 2 can be a long way away and you might have forgotten it. Okay, here you've got 3 atoms around each carbon. So it can take more, because remember we said it can have up to 4 bonds, which means it can have up to 4 atoms if they're singly bonded. So if I wrote this, okay, it's CnH2n, correct. So here it would be C2, and so 2 times 2 is 4, and you can see I've got 4. So it's got really 1 degree of unsaturation because it's got 1 double bond. Here, so you take it as if there were only single bonds. Yes, if you're looking at the degree of unsaturation, or degree of saturation, depending on which way you view it, is that if this was a single bond, I could have fit 4 atoms around here. At the moment, I'm only fitting 3 atoms around here. So it can take another atom. Does that make sense, April? Yep. So here, each carbon atom is attached to only 2 other atoms. So it can actually get 2 more atoms to surround it. Okay, so this is more unsaturated and correct. Okay, now for this sort of formula, it's either 1 triple bond like we've got here, or it could be 2 double bonds in the formula. So you'll have a thing of CnH2n minus 2. So 2 times 2 is 4, subtract 2, you're back to 2, and you can see I've got that. So let's look at some examples. Okay. Oh, okay, sorry, these are other formula if I have other atoms present. Okay. If I have oxygen or fluorine, chlorine, bromine, and so on, it doesn't affect that ratio of CnH2n plus 2 for saturated. 1 unsaturation is CnH2n, and 2 unsaturation is CnH2n minus 2. These have no effect. Oxygen being 2 bonds, it doesn't affect the ratio. And the fluorine, chlorine, bromine, iodine, we simply count it as part of the hydrogen atoms. So if I've got 5 hydrogen atoms and 1 chlorine atom, we count that as 6. Okay. And we'll look at examples. So, but nitrogen, because nitrogen can form 3 bonds, it affects the formula a little bit differently. So if it's saturated, instead of CnH2n plus 2, because nitrogen can form 3 bonds, it's going to be 2n plus 3. And if there's 1 double bond, instead of being CnH2n, remember nitrogen can form that extra bond, so it'll be 2n plus 1. And triple 1, instead of being CnH2n minus 2, it's CnH2n minus 1. And as I say, we won't deal with this very much for the exam, but you will look at it when we're doing the spectroscopy. Not so much for the exams, but if you know these formulae, it'll make it much easier when you do the spectroscopy. And as I say, this is only for excellence level. The spectroscopy standard is very easy to achieve. really you have to do very little to achieve it. But for excellence, they do expect a little bit more, actually quite a bit more. So the plus X is how many more atoms the atom in question could still take on. Yes, although I don't know, it depends on which way you take it, because this can't take, I mean, that's 2n plus 3. It doesn't mean it can take on more, 3 more atoms. Okay, this one's saturated. It won't take on any more. Here, the carbon, I agree, can take 1 more, but under the normal CnH2n, you can't do that. So I don't know if I'm misunderstanding you. Yeah. Okay. So the easiest, if you want to try and remember, the formula is to do these simple ones, and then that'll give you the formula. Okay. But I'm going to pretty much leave it there. Okay, I've got it over here, so we'll do this quick practice. So C3H6. This is a CnH2n. So do you remember, does it have 0, 1, or 2 double bonds? It actually has got 1, because if we go back a bit, remember to have 0 double bonds, we need CnH2n plus 2. Okay, so C3H6 comes over here, so it's got 1 double bond. Okay, so 1 C4H10. Would you like to have a go at that? Is this 0 double bonds, 1 double bonds, 0? Correct, because it's CnH2n plus 2. So C4, 4 times 2 is 8, plus 2 is 10. Number 3, C3H8, correct, 0, because 3 times 2 is 6, plus 2 is 8. Number 4, okay, correct, because remember the Cl you count as part of the hydrogen, so it's 8 in total, 7 of the hydrogens plus the chlorine. So C3 times 2 is 3 times 2 is 6, plus 2 is 8, and you've got 8 there. What about this one? Number 5. 1, correct, because remember the oxygen doesn't affect the ratio at all, so it's CnH2n. What about number 7? Number 6. Okay, correct. Wait. Yes, you're right. You're right. It's because it's CnH2n plus 1 if you've got a nitrogen present for 1 double bond. And, oh, sorry, I've clicked by mistake. And this you can see is 5 times 2 is 10 plus 1, because you've got a nitrogen present, means I've got 1 double bond. The oxygen doesn't affect it. Here, what is this one? Now remember the chlorines you count as part of the hydrogens. So it's like C6H12. So it's 1. Correct. Okay, and the last one? So C4H5, but remember the Cl is part of this, so it's C4H6. It's got 2, because 4 times 2 is 8. 8 subtract 2 is 6. Okay, so that's, as I say, it's not so important for the exam at all, but it is important for the spectroscopy for excellence. Okay, what I want to do now is the isomers. You have to learn 3 different types of isomers, of which you already know 2 from last year, so it's not so bad. Constitutional isomers, also known as structural isomers, you should have come across last year, and then also geometric isomers. Now, geometric is when you have a double bond, okay, and there's one other you have to learn this year, which is the optical isomers. Okay, so Joe, fine, you're catching up. Just keep on asking questions. Right, so what are isomers? They have the same molecular formula, but the atoms are arranged differently in space. Because remember, atoms are three-dimensional. And to change from one isomer to the other, you have to break a bond. I can't just simply twist the molecule to get another structure. That is not an isomer, okay, or certainly not the ones we're talking about. So you have to break a bond. So these two molecules, are these isomers of each other? Okay, so April, you're correct. Joe, trick question really, because it looks as though, oh, here it's on the end carbon, here it's on the other one, you had to break this bond to shove it across to the side. But what I've really done is I've just simply flipped the molecule. Okay, so there it looks as though they're different, but if I flip it, then it's identical. Okay, yep. So any rotation or bending or twisting is not an isomer if I get the same one. But if I break a bond and have to put it elsewhere, make it elsewhere, it is an isomer. So here's an example. Are these isomers? So April is typing and yep. Because what happens if I put it there, it doesn't matter which way I rotate it, I'm never going to get the OH on the second carbon to go into the first one without breaking, okay, I flipped it around like that, without breaking that and shoving it over there. I have to break that bond, and that hydrogen I have to then put back up here again. So that's an isomer, same molecular formula, so I've got to have the same elements, same number of atoms of each element, but they are connected differently to each other. So here the OH was on the second carbon, now it's on the first carbon. Okay, so you get two different groups of isomers that you have to know: the constitutional or structural isomers, and what we call the stereoisomers, where they have a different space. This is more about how they occupy their positions in space, and as I say, geometric is what you would have learnt at level 2, and then this one is a brand new one. So Joe, you've got a question mark. I'm not quite sure what you look up. Okay. Right. So you need to look it up yourself, or do you want me to? Oh, to the previous question. Oh, thank you. But they have different names, right? Yes. So isomers will have different names. So if you've flipped a compound and you get the same compound as before, they'll have the same name. But whenever you have to break a bond and make it elsewhere, you're going to get a different molecule, so it will have a different name. So you are going to, that's a good way of finding out whether you've got isomers or not. If your name is different, you'll have a different isomer. Just make sure your names are correct, of course. Okay, so here are constitutional isomers, so it's same molecular formula, but the atoms are connected differently, or the atoms are connected in a different order, something along those lines. Stereoisomers is they're arranged in the same order, so I'll have my OH on the same carbon atom, for instance, but it's going to have a different position in space, and there's no ways I can flip or do anything to that molecule to get it to occupy the same position in space. So it can be either geometric isomer or an enantiomer, optical isomers. So let's have a look at constitutional isomers. When we take our atoms, we can order them in all sorts of different ways. We can change the functional group, as long as we have the same elements, of course. We can move the functional group to a different position in the chain. So the OH could be on the first carbon, or the second, or the third, or whatever. We can vary the length of the parent chain. So we can have like pentane, or we could have 2-methyl butane. Okay, so there's ways of doing that, or 2,2 dimethyl propane. And we can put the side chains in the different position. So we could have 2-methylhexane or 3-methylhexane. So let's do an example here. That's my molecular formula. Okay, and what I've got here is I've got a double bond present. So I know I can form a CC double bond or a CO double bond as well. So you can have a whole variety of things. So here's one isomer I can draw, 1, 2, 3 carbons. You count, I've got 7 hydrogens, I've got 1 oxygen and a nitrogen. I could draw that as well. So this is an enol, an alkenol. I've got a double bond and a hydroxy group. This is what sort of functional group over here? Does anybody remember from last week? No, a ketone. So this is an amine and a ketone. So if you like, it's an amino ketone. Here, do you remember what this functional group is? An amide, correct. So can you see all what I'm doing here is I'm just taking my 3 carbon atoms and my 7 hydrogen atoms and my oxygen and my nitrogen, and I'm just rearranging them, I'm just connecting them differently, and I'm landing up with different functional groups. Okay? Okay, not a problem, Joe. You know, it's okay. Here I've got the same sort of thing as an enol, okay, a double bond and an alcohol, but what I've done here is it's actually an amino enol, but here I've got my OH on the end carbon instead of on the second carbon. Okay, so there's all different ways I can do it. Here I now have an aldehyde, so I took my NH2 from there and I put it onto that carbon. So if you get given a molecular formula, you could draw a wide variety of isomers. So the question might say, draw an isomer that shows acidic properties, okay, or basic properties. So if it's basic, you need an amine because that's basic. We haven't really done chemical properties yet. This is really more from last year, but when we do the next booklet, you'll know you've got to draw an amine. This is neutral, this will be basic, this will be basic. Anything with an amine will be basic. Okay, or they might say draw a neutral compound. Okay, in the booklet I drew more than we are. No, not necessarily, because sometimes these, as long as they're all different isomers and you aren't drawing the same molecule but sketched in a different way, then, so if you drew the same molecule but sketched in different ways, it's wrong. But if you've got all the different isomers, then that's not wrong. Because sometimes there's so many isomers you could draw at times. You would never be asked to draw all the isomers, because there would be quite a few isomers to draw for this. So here's an example, okay, and I'll just go through it. We know that a double bond is present, so we could draw, we've got an oxygen with a double bond, so we could draw an aldehyde, a ketone, an alkene, and alcohol. Could we draw a carboxylic acid? No, because a carboxylic acid has 2 oxygens, one for the carbonyl and one for the OH. Could I draw an ester? Not too sure? No, you're correct, you can't, because an ester has a C double bond O, and then it has that OR group as well, so it needs 2 oxygens as well. So if you get a formula and you know it's got a double bond present, okay, Joe, that's fine. You can have the recording, and as you do the booklets, it will come together. Okay, and as I say, I think April said she was using the Quizlets to learn the functional groups, and that's a good way of learning. Organic has got quite a bit of off-by-heart learning, so just keep on practicing. That's why I like doing organic a bit early in the year, so you've got a longer time to get your head around and learn all the functional groups and learn all the reactions before the exam. If you try and cram it just before the exam, you're going to have a tough time. Okay. Right, so if I was doing this, if I what's the exam? Yes, that's right. So draw 4 atoms in a row because I've got 4 carbons, add your functional group, okay, and as I add it to the first carbon if you can. This is if you want to go through a methodical way of drawing isomers, and then you fill the rest with your hydrogens and so on, and then you just move the functional group, then you shorten the parent chain and put in side chains, and you just keep on going. But as I say, you'll never be asked to draw all of them. But here's an example if we did. So I've drawn 4 carbons in a row, okay, I've added a functional group, I've made it an aldehyde, okay, and so if I carry on now, so that's butanol if I wanted to name it. Do I have to put the 1 in for butanol? Must I say butane 1L? No, because the aldehyde can only be on the first carbon. And if I drew that, because we know it's got to be on the end, is that the same molecule? Yes, and it's butanol too. So that is not an isomer. You have to simply drawn the same molecule. Okay. Now, if I can't draw, move the butanol, this anywhere along, but I could draw isomers of this by moving, doing this part here. Then do the same but with 3 carbon atoms and 1 side chain. So can you see I've got now 1, 2, 3, and I've taken the 4th carbon and put it on the 2nd. So that is 2-methyl propanol, because I've only got 3 carbons in a row and a side chain. Could I put this methyl group on the end carbon and make a different isomer? No, because then I make butanol again. Okay, so, well, that's all. I can only draw 2 aldehydes. I could draw a ketone, so I could put the C on the 2nd carbon, and it's a ketone because I've got a carbonyl attached to 2 other carbons. Okay, so now I have to put that number in. Actually, you don't have to really. You could say butanone, because if I move it onto this carbon, it's still butane 2O. So you could actually say butanone. It'll still be correct. And if I moved it over, then can you see it's still butane 2O? So butanone is correct. And I can't move anything further. I can't make a side chain because I can't put a carbon on here because this carbon's already got 4 bonds. So that's everything with the ketones. I can't draw any other ketones. Here I've tried to draw another one, but I hope you can see that's still butane 2O, so it's still not an isomer. Okay, so it's good to practice and draw it and then have a good look, name it, see if it comes up with the same name, and then you know whether it's an isomer or not. The more you practice, the more you'll go, I can recognize it as a different isomer. But if you don't practice, it's quite hard seeing straight away whether it's an isomer or not. Okay, I know Joe is typing there. Okay, why don't you use a double bond between the yes, we're going to. Okay, as I said, we can do aldehydes, ketones, and then the enols, which is what we're going to do now. So here it is. So I've made both functional groups on the first carbon. And but 1-ene, 1-ol. Okay, here I've moved the OH along, but I've kept the double bond where it is. So it's but 1-ene, 2-ol. Here I've carried on moving along, and it's a different name, but 3-ene, 2-ol. Because remember, the OH gets the lowest number possible. So I don't go 1, 2, 3, I go 1, 2, because the OH needs the lowest possible number, because it's the more reactive functional group. And then I can have that one, which is but 3-ene, 1-ol, starting numbering on this side. So here I've made the double bond between the first 2, and all I've done is I've simply moved the oxygen, the OH along, to see if I've got a different compound each time, and I do. Now I could move the the double bond along. So here it's exactly the same as this top one, except instead of having my double bond there, I've moved it along. Why but 3-ene, 1-ol? because the OH is the dominant functional group. You do need to learn the order. It's the carboxylic acid derivatives, and then you go down to the aldehydes and ketones. Okay, but why the N? Because of the double bond. If it was N, it means they're only single bonds, carbon-carbon single bonds. En means they are double bonds, and it's, if we're counting that this is carbon 1, then that's carbon 2, that's carbon 3. So we give the position of our double bond on the third carbon. No, this is not a triple bond, it's a double bond. There's only 2 lines. Okay, the same thing, we'd start counting from this side, 1, 2, 3. So the double bond is, we numbered always as the first carbon of the 2. So we say this is 2-ene and not 3-ene and not 4-ene. We don't go to the last one, we go to the first one. Okay. And as I say, for level 3 you don't get triple bonds. So here's one but 2-ene-1-ol, because now my double bond has moved on, but we have to give this the first number 1 because that's the dominant functional group. And now I can move my oxygens OH along. So here I'm just showing all the different variations you can draw, and they that one is the same as that. All I've done is twisted this to go down. Okay, right, Joe. And it is just about 4 o'clock anyway, so I think we're going to be, yeah, I think that's a good place to stop, because I'll do geometric and the other one. Okay, so see you next week, and I'll hope to finish the CH3051 next week, and then we'll go on to the reactions. So